The next thing to talk about is we're talking about another way. So we're off of genetic mutations now. Now we're going to start talking about ways that we can discuss how much damage radiation can cause. Okay, so we had units, right? We had the gray, the sievert, and those would tell us like how much radiation and then how much harm from radiation. This is another way to talk about how much harm radiation can cause. Okay, this is a concept called linear energy transfer, or LET. Okay, I'll explain, and I would love it if you guys would ask questions. It's great to ask questions here because this took some time to get. I've got videos on the YouTube channel specifically for these. If you haven't gone to them, I suggest that after I talk today, you go rewatch them. I bet you I say things on the video that I didn't say here and vice versa. But anyways, linear energy transfer, a way of measuring the harmfulness of radiation, is saying how much energy does the radiation, particle or electromagnetic, deposit along its path. Okay? You know, if you have X amount of energy and you deposit all of that energy over 1 centimeter, well, that energy is put into a more concentrated area than if X amount of energy gets deposited over 1 meter, right? If you deposit an amount of energy over 1 meter, well, that energy was more spread out. And in any one specific spot, there was less damage, okay? So, whereas the rad or the gray, this is an older PowerPoint, you can tell because it uses the rad as the unit, but the gray measures energy deposited it's per gram in this case, but per kilogram is how we really measure it. Coulombs per kilogram is the gray, right? How much energy per mass. Linear energy transfer, or LET, measures energy deposited over distance paths. These distance paths can be any arbitrary unit. You can say you deposit this much energy per millimeter, or you deposit this much energy per micrometer. It just depends on the type of radiation and what kind of numbers you want to get. Things to remember. A high linear energy transfer means that the energy deposited by the radiation was deposited into a small area over a short distance path, as in the energy is more concentrated. Okay? The opposite, a low linear energy transfer, means the energy from the radiation is deposited over a long distance path, as in the energy is more spread out. Linear energy transfer is an indicator for harm, for biologic harm, for how harmful the radiation is. Any unit of distance and any unit of energy can be used for this. You can convert kV, kilovolts, into many other units for energy, but we're going to keep it in kilovolts. We like kilovolts because in the X-ray room, we can put that into direct, contact with the X-ray machine, right? We say we set the energy of the X-ray beam by setting what factor on the control console?
What was it?
What factor on the control console do we set to change the energy of the X-ray beam?
Mass.
That changes quantity, right? KVP changes energy, quality, right? So you only have those two things, really, right? You have how much radiation do you make and how energetic is that radiation. So we use kV. We like kV because that lets us remind ourselves that we actually take and make that setting on the X-ray machine. We make a kV setting. So we say how much kV is deposited over how much distance. You can use any distance, right? Any fraction you want, but we're gonna like micron or micrometer best because it lets us have numbers that are like intelligible numbers that are not like super teeny numbers or super large numbers, right? Okay. Micron, by the way, micrometer is 1/1,000,000th, 1/1,000,000th of a meter. Okay, so let's use an example here, okay? On the left of this example, you've got X-rays, okay? And on the right of this example, you've got alpha radiation. What type of thing are X-rays? I said to think about them as a wave, right? Not a particle, but a wave, okay? meaning that they have no mass, no charge. They are simply a form of what's called potential energy. They carry energy, okay? Contrast that against an alpha particle. An alpha particle is what type of thing? I said it. So what type of thing is it? It's a particle, right? So there's particles or waves, okay? Those are the two types of ionizing radiation, okay? X-rays are waves. Alpha particles are particles. Alpha particles, remind yourselves, are massive, as in they're made of something, okay? They're made of protons and neutrons, and they carry an electric charge. They carry an electric charge of well, +2 if you're using, simple terms. Okay, massive charged versus massless uncharged, okay? They both start with the same amount of energy, okay? 80 kilovolts of energy, 80 kilovolts of energy, 80,000 volts of energy, okay? You are an X-ray photon. Let's say you travel, as the analogy says, you travel 6 micrometers before something happens. Francisco, what's happening here? Yeah, I use you because you said it earlier, right, when I talked about, X-rays preferring direction. You said an X-ray could scatter, right? That's a scatter event. What did it run into? This is a body, so human, so what's it most likely that it ran into? So you're a cell in a human, right? What are you mostly made of? Water. Water, right? So it's most likely that this scatter event was water, okay? What could have happened here when it scattered off this water molecule? Could have happened to the water molecule? Could have ionized it, creating an ion and a free radical, okay? A charged particle and an uncharged hydrogen free radical. Good. And that hydrogen free radical and that hydroxyl, hydrogen-oxygen molecule, they're going to go cause havoc somewhere in the cell, okay? So after that first scattering event, that ionizing event is going to cause some problems, okay? But don't care about that. We're ignoring that right now, ignoring that damage there. And we say that X-ray photon, after 6 micrometers, scattered, okay? Then traveled 8 micrometers and scattered again, doing the same thing again. Maybe this time it ran into DNA, okay? And then, so scatters and travels another 10 micrometers. After that last scattering event and hitting here, whatever it hit, it lost all of its energy, okay? The X-ray photon doesn't scatter any further. It's been absorbed completely, okay? So what we can say is that X-ray photon took 80 kV of energy and deposited that energy over a distance path of 24 micrometers, right? 6 plus 8 plus 10, okay? 80 kV over 24 micrometers, 80 divided by 24, is 3.3 kilovolts per micrometer path, okay? Every micrometer, there was 3.3 kilovolts deposited, okay? Go over to the alpha particle. The alpha particle comes in, enters the body, enters the cell, and whatever it hits, it immediately dumped all of its 80 kV immediately, okay? It only made it 3 micrometers into the tissue before it deposited all of its energy into the first thing that it hit. Why didn't it scatter? Because it's charged, okay? The charged particle runs into something and immediately joins up, links up with that thing, ionizes the thing, makes a bunch of other ionized particles that you're not being shown here. Remember, conservation of energy says that this 80 kV is not gone, okay? This 80 kV was just dispersed to other things, okay? But for the particle, it's gone. For the wave of radiation, it's gone. For this particle, that 80 kV has disappeared. That 80 kV got dumped into the atoms that it hit, and now those atoms are going to disperse that energy. But importantly, for that alpha particle, it's gone. Energy's gone. No more leftover energy. It deposited all 80 kV over 3 micrometers. 80 over 3 is 26.7 kV per micrometer. So the linear energy transfer for alpha radiation in this analogy, in this example, is 26.7. Okay, we chose units of kV per micrometer, and in those units, 26.7 is a lot bigger than 3.3. Okay, we would say that compared to X-rays, alpha radiation has a higher linear energy transfer. Okay, it deposits more energy more quickly over a shorter distance path. How do you guys feel about that? Intelligible? It's understandable? Yeah, okay. So we know what these LETs are. We know the LET, the linear energy transfer for different types of radiation, so let's just give them to you, okay? Diagnostic radiation in units of kV per micrometer, X-rays have a linear energy transfer of 3. We just showed you that, okay? 10 mega electron volt protons, mega is million, so 10 million volt protons have a LET of 4. So that's a higher linear energy transfer. Which one's more harmful? 10 megavolt protons or diagnostic X-rays? The protons are, right? The high energy protons are. Now, if we had super duper low energy protons, they would have a lower LET. Okay, but importantly, at this energy level, they are more harmful than X-rays. 5 megavolt alpha particles have a LET of 100. Why do these alpha particles have a way higher linear energy transfer than the protons do? What's different? Different charge, different mass, right? Even though these have a low, so notice this is 5 megavolts, versus 10 megavolts. Even though these have a lower total energy, the particle is so much larger, more massive, it's going to carry more kinetic energy with it, more momentum. And then in the particle accelerators, such as the Large Hadron Collider in Geneva, Switzerland, or Fermilab's particle accelerator here in the United States, which I think they turned off. Importantly, though, there's scientists make giant particle accelerators where they can smash atoms into each other and look at what happens when you do that. Look at what particles get created when you smash atoms together. These are called particle accelerators, and the particles that come out of these explosions, these interactions, are called heavy recoil nuclei, and they can have LETs as big as 1,000 because they're so high energy because they're traveling so fast. Things to take away from this: the more penetrating the radiation is, the lower the linear energy transfer is, okay? It is better for the radiation to travel further and deposit its energy over a longer path than it is for it to deposit its energy over a shorter path. X-rays are less harmful than most other types of radiation because of this. If X-rays did not have a low linear energy transfer, we wouldn't have diagnostic imaging, because in order to make an X-ray image, what does the X-ray beam have to do? Which means it has to go through the whole patient, right? Only a portion of the beam has to make it through the patient, but the beam has to get through the patient, right? There has to be a remnant beam. Remember, back to like principles of exposure. The remnant beam has to have image signal. It has to carry information about the patient, and if it doesn't make it through the body, it can't carry any information about the patient. So you can't make an imaging device out of alpha particles. You can't make an imaging device out of beta radiation. You can't even really make it out of gamma radiation. You have to make it out of X-rays, because X-rays are the ones that can pass through the body, carry information, and make it to the image receptor. The downside of that is that X-rays can harm the body on their path, but they do so to a lesser extent than most other types of radiation. All types of particulate radiation are going to be more harmful. Okay, this is one way to measure harmfulness of radiation. The next way to measure harmfulness of radiation is to take and measure what's called the relative biological effectiveness, or RBE. Okay? And this is sort of a different idea. This is not measuring energy deposited over a distance path. This is comparing one type of radiation to another. Okay? So the effectiveness of certain types of radiation in causing a specified effect or disease compared to X-rays. That's what you're doing. You're comparing X-rays to another type of radiation. So you're saying there's an effect. Let's talk about this effect and say how much radiation does it take to cause this effect in X-rays? And then how much radiation does it take to cause this effect in other types, alpha radiation, for example? Okay, so we have an example for this. So you ask, what is the relative biological effectiveness of alpha radiation in destroying 50% of the body's epithelial cells? A sample of tissue, you take and irradiate it with alpha rays. How much does it take to kill half the cells? Okay? So, experimentation on animals and other things shows that it takes 2 grays of alpha radiation to destroy half of the cells. But when the same cells are exposed to X-rays, it takes 6 grays to kill them. So it takes more radiation by X-rays than it takes from alpha radiation. In linear energy transfer terms, why is that true? Why is it true? So which takes more to cause the effect? X-rays. It takes more X-rays than it takes alpha radiation. Specifically, it takes 3 times as many X-rays, okay? Why does it take more X-rays than alpha rays to kill half of those epithelial cells? Because the lead is lower for X-rays, right? So the fact that X-rays have a lower linear energy transfer than alpha radiation means X-rays are less harmful than alpha radiation, right? So you want to cause harm with one versus the other, you could use less alpha radiation to cause the same amount of harm as it would take much more X-rays to cause that harm, to cause that effect, okay? So the formula is really straightforward, right? Take the effect take the effect you want, talk about it, say how many grays does it take to cause that effect in X-rays, and put that at the top. How many grays does it take to cause that effect in the other type, alpha radiation, and put that in the denominator, the bottom. 6 divided by 2 is 3. The relative biological effectiveness of alpha radiation is 3 when compared to X-rays. That is to say, alpha radiation, as it says here, is 3 times more effective at cell killing than X-rays are. Alpha radiation is more harmful. Alpha radiation also has a higher linear energy transfer, so there's a relationship. If linear energy transfer is high, the relative biologic effectiveness should also be high. Okay. So here's your RBEs for typical types of radiation. Diagnostic X-rays have an RBE of 1. What is that saying? If diagnostic X-rays have an RBE of 1? What are you comparing these radiations to? Go back to this slide. What are you comparing the radiation to? Yeah, you're comparing it to X-rays. You're comparing apples to apples, right? An apple is no more apple-y than an apple, right? 2 apples are just one apple than another apple. So if you're comparing apples to apples, there's a 1-to-1 relationship here, right? You're comparing X-rays to X-rays, apples to apples, okay? In these other ones, the number is going to be higher than 1. So X-rays have an RBE of 1 because the comparison is comparing a type of radiation against X-rays, okay? In this case, you're comparing X-rays to X-rays, apples to apples, so 1-to-1. But other things, 10 megavolt protons, RBE of 5, 5 megavolt alpha particles, RBE of 20. By the way, this is where we got in earlier lectures where we said X-rays are, alpha radiation is 20 times more harmful than X-rays. It's this right here. It's the RBE for alpha radiation is 20 versus X-rays being 1. Alpha radiation is more harmful. Those heavy recoil nuclei, RBE of about 30. Okay, so that was linear energy transfer and RBE, and you can see that they're related to each other. Okay, if there's a high linear energy transfer for a type of radiation, then it probably also has a high relative biological effectiveness. And again, of course, vice versa.